Hi, it's time for another math easy solution. Today we're going to discuss, well, further into continuity. I did an earlier video a while ago actually on continuity, but it was a brief overview of it. I didn't really go too in depth in it. I did it on it and also on close and open intervals. Just make sure you watch out in the video link below. I'm going to go over it in more detail right now. Well, basically continuity, the mathematical definition of continuity, it corresponds closely with the meaning in everyday language here. So in an everyday language, a continuous process is basically one that takes place gradually without interruption or abrupt change, and this is similar to the mathematical definition. And the mathematical definition, well, we'll look at it right now. Basically, a function f is continuous at a number a, put this as separated from this a, if you have the limit as x approaches a of f of x equaling to, well, f of a right here. And now this definition actually implicitly requires three things, and those three things that it implicitly requires, just I'll have it listed right here. So this one, you need to have f of a has to be defined. That is, a is in the domain of f. So when you plug it in right here, you're going to actually have a value when you just plug in whatever the a is right here. And also that the limit as x approaches a of f of x exists. See video link below on I have a couple of videos on whether a function exists or not, if it's defined, etc. But now, and also if so, this one has to exist, and it follows that it has to be equal to f of a right here. So it just implicitly requires that f of a has to be defined. So this has to be defined, and this has to exist, and they have to be equal to each other. So that's just a way of writing it here. And we say a function is discontinuous otherwise if it doesn't follow any of these three things right here. Let's put that over there right here. And I'll illustrate this in a graph. So if I just draw these x and y axis right here. So now to draw a continuous function, basically if you just draw with a pen, if you never really lift it off, then that means it's a continuous function right here. So if we were looking at a, so I'm drawing a continuous one right here. This is a. So as you're approaching a, from any direction, you're basically gradually changing this f of x function. This is f of x, and at this value right here, we'll draw it over here somewhere, this is going to be f of a. So as you can see from the everyday language, its continuous process one takes place gradually without interruption or abrupt change. So as you can see, we gradually change right here, and as you gradually and smoothly basically get closer in a in this x-axis, this just gets closer and closer to this f of a right here, and this f of a is defined right here. So you plug in a, you're just going to get this exact value. And for this function, we just call it, well, in this case, continuous at a. So now if we look at places where it's not continuous, or we call it discontinuous or not continuous cases, we just look at each one of those three requirements and see if each one is not true. So for case a, if f of a is not defined, so if you have a function like this one right here, so this is a circle right here at the a, and this is at a. So as you can see, the circle means it's not defined. You can't plug it in right here. So then if this is f of x, thus it's not continuous, or it's discontinuous at a here. So that's the first case, if it's not defined. And now the second case, if the limit as x approaches a of fx does not exist. So one way of it is this: if you have something like this one right here, let's say f of a is right at here, but it's like a two-part function. So this is a, but then you have something like right here. So an open basically an open circle, which means it's not it's not defined there, it's defined here. So if this is your function, it's a two-part function right here. So the limit does not exist because the left-hand limit and the right-hand limit don't correspond to the same function right here. If this is f of a right here, this is going to be f. This is the limit as x approaches from the right side, as x approaches from the left side. So then this basically is not continuous. So this is another form of discontinuity. So now if you have this one here, this last case, well, if this is basically the definition, if it's not equal to f of a right here, but if both limits, if the limit exists right here, which is case 1 and 2, and then I mean requirement 1 and 2. So requirement 1 and 2, if this is defined here, and this exists right here. So but it's still, if they don't equal each other, then it's not continuous. So one example of this is if you have something that looks like this, looks like the first case, except you're defined right here. So as you can see, this one here, if this is A, right here, this is A and this is f of A, so f of A is defined, so the first requirement is met, and the second requirement is met as well, because this exists. Because as you approach x from both sides, so you're approaching x towards A, you're going to go to this limit right here. So this is the limit as x approaches A of f of x, but it's not equal to f of A right here. So this is f of A, and this one, I'll just cross it over here, is that. So they don't equal each other, and this is not continuous. And yeah, that's all for today actually on this. Hopefully you learned about this discontinuity, continuity, and basically the cases for discontinuity, and basically and also these three requirements. But that's all for today. Hopefully you learned from this. You can download these notes in Dropbox link below. I'll do some examples in later videos, but this is pretty straightforward discontinuity, and hopefully you'll learn from this. And yeah, stay tuned for another math easy solution.